please subscribe to support the channel. There is an explosion in the universe so absurdly rare that, as far as we can tell, our entire species has only ever caught one really clean example. And yet, some of the atoms in your rings, your phone, maybe even the metal in your blood were born in that kind of blast. Not the usual star death fireworks you've heard about, not a supernova that shows up in a pretty Hubble picture, but a quieter, shorter, nastier kind of detonation where two ultra-dense stellar corpses slam together, briefly light up a galaxy, and vanish, leaving behind nothing but fading red light and a spray of newly forged heavy elements drifting between the stars. The rarest thing in the universe that you've probably never heard of might literally be sitting on your finger. Let's start by being slightly rude to supernovae. Supernovae are iconic, but by cosmic standards, they're not that rare. In a Milky Way-sized galaxy, you expect core collapse supernovae, those made by dying massive stars, to happen a few times per century. Add in type 1a supernovae, the white dwarf explosions, used as standard candles in cosmology, and you get a steady background of boom. Spectacular, yes. Special, no. If you could speed up time and watch a typical spiral galaxy for a million years, supernovae would pop off like occasional camera flashes at a concert. Kilonovae, by contrast, are like the one shy fan in the back who only raises their phone once in the whole show. We think that in a galaxy like ours, neutron star mergers, the main engines behind kilonovae, happen on the order of once every 10,000 to maybe 100,000 years. That estimate comes from a mix of approaches: how many binary neutron star systems we see in the Milky Way, how fast their orbits are shrinking, and how often gravitational wave detectors like LIGO and Virgo hear the final in-spiral chirp. When you fold all that together, you get a rate so low that a civilization with only a few centuries of serious astronomical observations is lucky to see even one nearby event with modern instruments. So what is a kilonova in plain language? Take two neutron stars, objects about 1 to 2 times the mass of the sun, squeezed into spheres only about 20 kilometers across. Let them orbit each other for millions or billions of years, slowly radiating away energy and gravitational waves so the orbit shrinks. In the final moments, their orbital speed becomes a hefty fraction of the speed of light. Then gravity wins, the stars smash together, and things get weird. Some of the neutron star matter is torn off and flung outward in tidal streams and plumes. Some falls into whatever compact remnant is left, often a black hole. The stuff that escapes is insanely neutron-rich and initially incredibly hot. Over the next days and weeks, that debris glows as radioactive isotopes decay, dumping energy into the expanding cloud. That glow, powered by the decay of freshly made heavy nuclei, is the kilonovae. In terms of brightness, a kilonova lives in a strange middle class. It's much brighter than a classical nova, the kind of outburst you get from a white dwarf stealing material from a companion star, which might be 10,000 to 1,000,000 times fainter than a supernova. A kilonova peaks roughly 1,000 times brighter than a classical nova, so you could see a nearby one with a decent telescope. But compared to a typical supernova, it's still dimmer and shorter-lived. A supernova can stay bright for weeks to months. A kilonova evolves on a much faster schedule, bright within hours, changing color within days, fading away within a couple of weeks in optical light, and hanging on a bit longer in infrared. The color part is important. Early on, a kilonova can look surprisingly blue, hot, relatively transparent ejecta, radiating like a smooth thermal source. But as time passes, heavy elements in the expanding cloud make the material more opaque, especially at shorter wavelengths. The light gets trapped, reprocessed, and emerges at longer, redder wavelengths. So a textbook kilonova is a quick change artist. Day 1, a bright blue spark. By day 3, already shifting toward red. And by a week or two, most of the action has slid into the infrared, where many older surveys simply weren't watching. If your telescope is tuned mostly to optical light and you don't look at the same patch of sky every night, that blue phase might come and go between your snapshots, and by the time you look again, the source is faint and red and easy to confuse with all kinds of other boring stuff. That's one huge reason we didn't spot these things earlier. The universe doesn't announce them with big neon signs, and our observing strategies were optimized for slower, brighter transients. Traditional sky surveys might return to a given area every few nights or even every few weeks. For supernovae, that's fine. They evolve slowly enough that you still catch plenty of light. For kilonovae, that cadence is like trying to study a lightning bolt with one photo a minute. By the time you realize something happened, most of the interesting structure is gone. On top of that, kilonovae tend to be relatively red after the first couple of days, while many classic surveys were more sensitive to bluer optical wavelengths. So kilonovae were hiding in exactly the corner of parameter space where our instruments and habits were weakest: fast, faint, and red. There's also the confusion problem. The sky is full of transients that kind of look like what theory predicts for a kilonova. You can get fast-evolving, weirdly colored light curves from all sorts of phenomena. Unusual supernovae, eruptions of massive unstable stars, flares from accretin black holes, even bizarre outbursts from stellar binaries. When wide-field surveys started turning up more and more strange, short-lived events, kilonova models suddenly had lots of contenders. But most of them, once you got detailed spectra and more data, turned out to be imposters, not mergers of neutron stars, but some unrelated explosion wearing a similar light curve costume. That's why JW17018 and its optical counterpart AT2017 GFO are treated as the canonical kilonova. Before that, there were hints, extra infrared light after certain short gamma ray bursts, for example, that didn't fit the usual afterglow models and seemed consistent with a kilonova component. Those were tantalizing, but the data were sparse, maybe a couple of observations, days apart, no gravitational wave confirmation, no early time blue phase. You could argue about them, and people did. Then, on August 17th, 2017, LIGO and Virgo recorded the gravitational wave signature of a binary neutron star in spiral. Just 1.7 seconds later, gamma-ray satellites picked up a short burst from the same part of the sky. Astronomers scrambled, pointed telescopes at the rough localization region, and found a brand new point of light in a galaxy called NGC 4993. Over the next days and weeks, its brightness and colors evolved exactly like the best kilonova models predicted. Blue, then red, then fading into the infrared. For once, everything lined up. Gravitational waves, gamma rays, optical and infrared light, all telling the same story. This was not just some odd transient, this was the thermal afterglow of radioactive ejecta from a neutron star merger. And here's where it gets wonderfully absurd. That one event, that one single clean kilonova, is currently doing an outrageous amount of scientific heavy lifting. It's the benchmark for how bright kilonovae are, how their colors evolve, how much mass they eject, and which elements they likely produce. From its light curves, astronomers inferred something like a few hundredths of a solar mass of neutron-rich material blown into space, enough heavy elements to make tens of thousands of Earth's worth of precious metals. Plug numbers like that into models of galactic chemical evolution and multiply by plausible merger rates, and you can explain a big chunk of the gold, platinum, and other art process elements in a galaxy like the Milky Way. That means when you look at a gold ring, you're looking at the end of a ridiculously long and rare chain. Two massive stars had to form in the same system, live brief, violent lives, and each explode as a supernova. Their cores had to survive as neutron stars, remain bound in a binary, and slowly spiral together for hundreds of millions or billions of years. When they finally merged, the collision had to be just right to fling out enough neutron-rich matter. That ejecta had to cool, mix into the interstellar medium, get incorporated into a new molecular cloud, and then into the protoplanetary disk that formed the Sun and its planets. Some fraction of those heavy atoms ended up in Earth's crust, where geology and human stubbornness slowly concentrated and dug them up, smelted them, purified them, and turned them into something decorative. The rarest kind of explosion in the universe left fingerprints on something you can casually drop down a drain. So when we say a kilonova is rarer than a supernova, we're not just playing with statistics. We're pointing at a specific kind of event that is rare in occurrence, rare in observability, and yet absurdly influential. Supernovae give you lots of light and plenty of iron. Kilonovae give you a much briefer, subtler glow, and the universe's supply of cosmic jewelry. For now, nearly everything we think we know about them comes from one pristine case and a small supporting cast of maybes. It's like trying to understand all of biology from a single perfectly preserved fossil and a handful of weird bones. But that's the game astronomy often plays, taking tiny scraps of light from rare events and using them to rewrite entire chapters of the universe's origin story. If kilonovae are the rarest bombs in the universe, then neutron stars are the warheads packed inside them, quietly orbiting each other for ages, waiting for gravity to light the fuse. To really feel how absurd a kilonova is, you have to zoom in on the ingredients, because a neutron star is not just a dense thing. It's matter pushed so far past normal that our language breaks before the physics does. Start with this mental compression exercise. Take the sun, 1.99 times 10 to the 30th kilograms of hot plasma, and cram something like 1 to 2 suns worth of that mass into a ball only about 20 kilometers across. That's roughly the size of a city. You have just built a neutron star. If you could somehow scoop out a teaspoon of neutron star matter and bring it home without instantly annihilating yourself and the neighborhood, that teaspoon would weigh about 1 billion tons on Earth. 1 billion tons in a spoon. At that density, everyday substances don't make sense anymore. Atoms are crushed, electrons are rammed into protons, and the whole thing becomes one gigantic nuclear object, a titanic nucleus, stabilized by gravity itself. Inside, layers stack up in increasingly exotic ways. At the surface, you might still have a crust where nuclei and electrons exist in something like recognizable forms, just extremely packed. Deeper down, electrons are forced into protons, producing neutrons and neutrinos. The neutrinos escape, the neutrons stay. At even higher densities, neutrons themselves may pair up into superfluids. Protons form superconducting phases, and exotic particles like hyperons or condensates of mesons might appear. We're not completely sure because there is no lab on Earth that can reproduce the combination of density and pressure you get inside a neutron star core. Particle accelerators can touch similar densities for tiny fractions of a second. Neutron stars hit that and hold it for millions of years. They are nature's permanent high-pressure experiment, built once and left to stew. You might reasonably ask, if gravity is so keen on crushing matter, why not just keep going until you get a black hole every time? That's where the Tolman-Oppenheimer-Volkoff limit, the TOV limit, steps in. It's the maximum mass that neutron star matter can support against gravity without collapsing into a black hole, given a particular equation of state, basically a relationship between pressure and density for ultra-dense nuclear matter. The TOV limit isn't a single exact number. It depends on how stiff or squishy you think nuclear matter is at those densities. But observations, especially when combined with gravitational wave data from events like JWST 0817, constrain it to be around 2.0 to 2.2 times the mass of the Sun. Below that, neutron stars can exist. Above that, gravity wins completely and you get a black hole. This limit is a gorgeous example of theory meeting cosmic data. You take general relativity, write down the structure equations for a spherically symmetric star built out of some hypothetical nuclear matter, plug in your favorite microphysics for the equation of state, and out pops a maximum mass. Then you go to the sky and look for neutron stars, particularly heavy ones, like those in certain pulsar binaries, measure their masses, and see which equations of state are still allowed. Add in JWST 0817. The gravitational wave signal told us the total mass of the merging neutron star binary and how squishy the stars were as they tidally distorted each other. The kilonova and later electromagnetic signatures told us the remnant didn't survive as a stable neutron star for long. Put together, that means neutron stars cannot be arbitrarily massive and their matter can't be too stiff, or they would have resisted collapse. A cosmic train wreck becomes a measurement of how hard you can squeeze matter before it gives up and forms a black hole. Even before they merge, neutron stars are already extreme on another axis: magnetism and spin. Many neutron stars we see as pulsars spin dozens to hundreds of times per second. Some millisecond pulsars rotate around 700 times per second, meaning a mountain on their surface, if such a thing can exist, would be whipped around at something like a tenth the speed of light. Their magnetic fields are equally ridiculous. A normal pulsar might have a magnetic field strength around 10 to the 12th Gauss. For context, Earth's magnetic field is about 0.5 Gauss. That's a factor of 2 trillion difference. Magnetars, the drama queens of the neutron star family, can push into the 10 to the 14th or 15th Gauss regime. In fields like that, quantum electrodynamics gets weird. The vacuum behaves like a birefringent medium, and atoms are distorted into needle-like shapes along field lines. These aren't just magnets, they're cosmic particle accelerators and quantum laboratories wrapped into one. Now take two of these objects and bind them in a binary. That's not hypothetical. We've actually found several such pairs in our own galaxy. One example is PSR J1946 plus 2052, a double neutron star system with an orbital period of just about 1.88 hours. Two city-sized sun mass objects orbiting each other faster than many people's laundry cycles. The system is slowly losing energy by emitting gravitational waves, tiny ripples in spacetime. As it does, the orbit shrinks. We can measure that shrinkage with exquisite precision via timing the radio pulses from one of the stars, and the rate matches Einstein's general relativity predictions to absurd accuracy. Given the current rate of orbital decay, PSR J1946 plus 2052 will merge in about 46 million years. That's not long in galactic terms. We are literally watching a future kilonova in the making preheat in real time. These double neutron star systems are the seeds of kilonovae, but they're also stress tests for our understanding of gravity and matter. On the gravity side, every precisely timed pulsar orbit is a little laboratory for general relativity. You can see periastron precession, the orbit rotating due to relativistic effects, energy loss to gravitational waves, Shapiro delay as pulses pass through the companion's gravitational potential. On the matter side, every measured neutron star mass chips away at the space of allowed equations of state. Discover a heavier neutron star, and you immediately rule out any model of nuclear matter that would collapse at that mass. This is where the stakes start to feel almost philosophical. On paper, nuclear physicists and astrophysicists can write down many different equations of state that look reasonable. Fancy models involving nucleons, hyperons, quark matter, superfluid phases, and more. On a blackboard, lots of them work. But the universe does not care about what looks pretty on a slide. It cares about what actually happens when you stack up 10 to the 57 nucleons in a gravitational well. Every real neutron star is the universe's way of grading our homework. If your equation of state predicts a maximum mass too low, it's wrong because we see heavier neutron stars. If it predicts a star that would be too fluffy, it's wrong because JWST 's tidal signatures say neutron stars are more compact. And each kilonova is like the final exam version of that test. The moment where matter at the very edge of stability is slammed, ripped, and partially ejected, exposing its inner character in both gravitational waves and light. So when two neutron stars finally do meet and produce a kilonova, it's not just two dense objects collide in some generic sense. It's the culmination of everything tricky and uncertain about ultra-dense matter, gravity, and magnetism. Those city-sized balls of nuclear matter have spent millions of years quietly tracking out the predictions of general relativity as they spiral in. Their internal structure has silently encoded the correct equation of state in their sizes and masses. And at the moment of collision, all of that hidden information erupts into observable form. The gravitational wave signal encodes how they deform and merge, while the kilonova light encodes how much matter they eject, how neutron-rich it is, and what elements it forms as it decays. Every rare kilonova is the universe taking our neat theoretical models, slamming them into each other at relativistic speeds, and seeing what survives the impact. Now that you've met neutron stars as the universe's most ridiculous bricks of matter, it's time to watch what happens when gravity straps two of them together and slowly tightens the leash. On human timescales, a binary neutron star system looks calm and eternal, two invisible points gently orbiting. On cosmic timescales, that calm orbit is actually a death spiral, a very long, very slow fall where energy leaks away into the fabric of spacetime itself. The basic problem is that you can't have two massive objects orbiting each other in general relativity without shaking spacetime a little. Their motion creates gravitational waves, ripples in spacetime that carry energy away. Energy has to come from somewhere, and in this case, it comes from the orbit itself. As the waves radiate outward, the stars lose orbital energy and angular momentum, causing their separation to shrink. The orbit doesn't decay because of friction or air drag or anything intuitive like that. It shrinks because the system is literally shouting into spacetime and paying the energy bill. We've actually seen this happening, long before LIGO ever turned on. The famous Hulse-Taylor binary pulsar, PSR B 1913+16, has an orbit that is gradually shrinking over time. By timing the radio pulses with absurd precision, astronomers measured how fast the orbit is decaying and found that the rate matches Einstein's general relativity predictions to better than 1%. Other double neutron star systems show the same thing. Their orbits are slowly tightening at exactly the rate you'd expect for gravitational wave energy loss. It's like watching the second hand on a doomsday clock, except the seconds are millions of years. At first, that decay is glacial. Take our earlier example, PSR J 1946+2052 with its 1.88-hour orbit. Right now, those stars are still comfortably separated, whipping around each other, but not yet on the brink. Over millions of years, though, that period will drift downward. 1.88 hours, 1.5 hours, 1 hour, 30 minutes. The closer they get, the faster the decay. General relativity is merciless. As the stars move in, not only do they orbit faster, they also radiate more strongly, which makes the orbit shrink faster, which makes them radiate more strongly, and so on. It's a runaway process toward merger. Near the end, things go from cosmically slow to this escalated quickly in a hurry. The orbital period plunges from minutes to seconds to milliseconds in the final stretch. Just before they collide, the stars are separated by only a few tens of kilometers, moving at a decent fraction of the speed of light. Picture two city-sized objects, each more massive than the sun, circling each other hundreds of times per second. The distinction between orbiting and falling dissolves. They're doing both at once. This is the stage where instruments like LIGO and Virgo finally come into play. They don't see the stars, they feel the changing gravitational field as the orbit tightens. To them, the in spiral is a steadily rising note, a chirp in frequency and amplitude. In the case of JWST, the gravitational wave signal spent about 100 seconds sweeping from around tens of hertz up into the hundreds. Lower frequencies correspond to earlier, wider orbits, higher frequencies to the rapid whirl just before collision. The closer the stars get, the faster they orbit, the higher the wave frequency, the louder the signal. If you turn that data into sound for outreach, you literally hear a rising whoop, a cosmic slide whistle played on spacetime. The shape of that chirp is priceless information. It encodes the masses of the two neutron stars, their spins, and, crucially, how much they tidally deform each other as they approach. A perfectly rigid point mass would produce one kind of chirp. A squishy, easily distorted star produces another. By fitting the observed chirp with theoretical waveforms, you can extract how squishy neutron stars are, which feeds back into their equation of state. So even before any light appears, the death spiral is already telling us about the interior physics of ultra-dense matter. But gravity is greedy, and as the stars get really close, tides start to tear at them. Just like the moon raises tides on Earth, each neutron star raises tidal bulges on the other, except here the tidal forces are strong enough to literally rip matter off the surface. In the last few orbits, these bulges stretch and shear, and chunks of neutron-rich material get flung outward in spiraling tails. Some of that matter is dynamically ejected during the merger itself, More can be blown off later by winds from the hot, swirling accretion disk that forms around the remnant. Simulations suggest you can easily throw out around 0.01 to 0.05 solar masses of material in this process. That's 1% to 5% of the sun's mass, launched at speeds of about 10% to 30% of the speed of light. For something that started out as hypercompressed neutron star matter, that's an enormous amount of stuff suddenly allowed to expand and cool. Observations of JWST-0817's kilonova light curve, AT 2017 GFO, actually lean toward the higher end of those ejecta masses, around that 0.05 solar mass figure. That's roughly 16,000 Earths worth of heavy element material getting sprayed into interstellar space in a single event. Once this matter is out in the open, no longer under neutron star pressures, it begins to unravel. It's still incredibly neutron-rich, and at those densities and temperatures, nuclei start capturing neutrons in the rapid-fire way we talked about earlier, the arc process. Nuclei climb up the mass ladder, becoming heavier and heavier until they can't hold all those neutrons, and begin to beta decay back toward stability, spitting out electrons and neutrinos. The decay energy heats the ejecta from within. That hot, expanding, radioactive debris cloud is what powers the kilonova's glow. The geometry of that ejecta matters too. Some of it is flung out in the equatorial plane from the tidal tails, very neutron-rich, packed with elements like lanthanides that make the material opaque and favor red and infrared emission. Some is blasted out more toward the poles in winds from a hypermassive neutron star or accretion disk, where neutrino irradiation can change the neutron-to-proton ratio and create a bluer, less lanthanide-rich component. The final light you see depends on which parts of this messy 3D structure you're looking through. But the core idea is simple. In the last milliseconds of the inspiral and the first milliseconds after impact, gravity tears neutron star matter loose. That matter undergoes runaway neutron capture and radioactive decay, and the result is a cooling, glowing, expanding fog of freshly minted elements. This is the exact hinge point where the story stops being pure gravity and becomes cosmic alchemy. Up to the moment of collision, you can describe almost everything with general relativity and orbital dynamics, two point masses spiraling inward, losing energy to gravitational waves. It's a beautiful, clean problem in mathematical physics. The chirp LIGO hears is, in a sense, gravity singing to itself. But the instant matter starts getting ripped out and flung away, you've created a laboratory for nuclear physics and chemistry. Those ejected neutrons and nuclei don't care about our tidy categories. They just follow the rules of quantum mechanics and the weak force, assembling elements the universe will use billions of years later in planets, oceans, electronics, and organisms. So, when a kilonova happens, you're not just seeing two dead stars merge. You're witnessing the transition from invisible space-time ripples to visible, element-forging fire. In the first act, gravitational wave detectors silently record the inspiral, extracting masses and tidal deformabilities from the pattern of a 100-second chirp. In the second act, telescopes across the electromagnetic spectrum rush in to watch the radioactive aftermath as that shredded matter cools and recombines. The death spiral is the bridge between those acts. The razor-thin moment where a purely gravitational story explodes into a thermonuclear, chemical, and ultimately personal one. The ripples in space-time that started this whole thing end up writing atoms that can sit in a human hand. By the time two neutron stars hit the final frantic orbits of their death spiral, the universe is already broadcasting the ending long before any light appears. The problem is, those broadcasts aren't in a language our eyes understand. They're in gravity. To eavesdrop on that conversation, humans had to build some of the most absurd measuring devices ever constructed. Instruments that can sense distortions in space-time smaller than a proton across a machine the size of a small town. That, in essence, is what LIGO and Virgo are. Picture two vacuum tunnels laid out in an L shape, each arm 4 kilometers long in the case of LIGO. A laser beam is split and sent down both arms, reflects off mirrors at the ends, and comes back to recombine. Under normal circumstances, the beams interfere in such a way that the detector sees almost no light. But if a gravitational wave passes through, it stretches one arm a tiny bit and squeezes the other by a tiny bit, changing the travel time of the light. That shifts the interference pattern, and some light leaks through to the detector. The scale of the distortion is ridiculous. We're talking about changes in length on the order of 10 to the 19th meters over 4,000 meters. That's like detecting that the distance between Earth and the nearest star changed by the width of a human hair. When LIGO first switched on in advanced form, the universe greeted it with not neutron stars, but black holes. In 2015, it picked up gravitational waves from pairs of black holes spiraling together and merging. Those signals were short, fractions of a second, and loud by gravitational wave standards. They were also dark. Black holes don't have surfaces or atmospheres, so when they merge, you get an enormous gravitational wave splash, but essentially no light. For a while, gravitational wave astronomy was kind of a silent movie, stunning in what it revealed about invisible, massive objects, but with no electromagnetic color commentary. That changed on 17 August 2017. LIGO and its European cousin Virgo picked up a new signal, labeled JWST-0817. Unlike the brief, thumpy black hole mergers, this one was a graceful, drawn-out chirp, about 100 seconds of rising frequency and amplitude as two neutron stars spiraled together. From the waveform alone, scientists could tell this wasn't black holes. The masses were lower, in the neutron star range, and the tidal effects imprinted subtle differences on the chirp. By matching the signal to theoretical templates, they estimated the source was about 140 million light-years away in the general direction of the constellation Hydra. Then the universe added a plot twist. 1.7 seconds after the end of the gravitational wave signal, two space-based gamma-ray observatories, Fermi and Integral, recorded a short gamma-ray burst from roughly the same part of the sky. Short GRBs had long been suspected to come from neutron star mergers, but this was the first time we'd seen one practically on top of a gravitational wave detection. The mere existence of that 1.7-second delay between gravity wave hits us and gamma rays hit us carried a ridiculous amount of information. Here's why that delay is such a big deal. Both gravitational waves and light had traveled roughly 140 million light-years to get here. That's about 1.3 times 10 to the 15 seconds of travel time. If they arrived within 1.7 seconds of each other after that journey, their speeds must match to within roughly 1 part in 10 to the 15. In other words, the speed of gravity is the speed of light to insane precision. That single measurement nuked an entire zoo of modified gravity theories that predicted different speeds for gravitational waves or frequency-dependent propagation. Ideas that had been debated in papers for years evaporated with one timestamp. Meanwhile, the detection geometry gave astronomers a clue about where to look. LIGO has 2 detectors in the United States, and Virgo in Italy added a third ear. Gravitational waves don't hit all 3 at exactly the same moment. They arrive a few milliseconds apart, depending on where the source is on the sky. By comparing these arrival times, you can triangulate a rough position. It's like hearing thunder at different times at different weather stations and working backward to find the lightning bolt. That triangulation didn't give a tiny dot, but it did narrow things down to a patch of sky only a few tens of square degrees. To your eyes, that's still enormous, but to astronomers used to the entire sky being 40,000 square degrees, it's a miracle of narrowing. It meant that instead of hopelessly scanning the whole universe, telescope teams could compile a list of galaxies in that volume and start checking them, one by one, for anything new that had appeared since the last time they looked. What followed was a global treasure hunt. Observatories in Chile, the United States, Europe, and beyond swung into action. Within about 11 hours, a small telescope in Chile, the SWOPE telescope, found the fresh point of light in a lenticular galaxy called NGC 4993. exactly where the 3-detector gravitational wave localization allowed it to be, and at just the right brightness to be the afterglow of a neutron star. That source was cataloged as SSS-17A AT2017 GFO, and it soon became clear it was not a normal supernova, not a flaring star, not anything mundane. Its color and brightness evolution matched the expectations for a kilonova frighteningly well. All of this, from the 100-second chirp to the 1.7-second delay, to the telescope zeroing in on one galaxy in a sea of possibilities, marked the shift in how we talk about gravity. Before, general relativity was well tested in the weak fields of the solar system, in binary pulsars, and indirectly in cosmology. We had good reasons to trust it, but there was room at the edges for alternatives. After JWST 0817, gravity stopped being just a neat geometric theory written in textbooks and became something you could treat like a measurable signal with a speed, an amplitude, and a direct comparison to light to 15 decimal places. And the thing that makes it perfect for our story is that the same event that nailed the speed of gravity also lit up in every other way you care about: gamma rays, optical light, infrared, X-rays, and radio. We didn't just hear the universe whisper through space-time, we watched the fallout as neutron star matter was torn apart and turned into heavy elements. JWST 0817 is where pure gravitational wave astronomy collided head-on with dirty, glowing, element-forging astrophysics. From that point on, kilonovas weren't just theoretical footnotes. They were the visible aftermath of a signal we could literally listen to. By the time telescopes swung toward the patch of sky flagged by JWST 0817, the crucial gravitational wave physics had already happened. The neutron stars had merged, the space-time ripples were on their way out into the cosmos, and somewhere in a quiet galaxy 140 million light-years away, a radioactive fireball was blooming. All that remained for us was the cosmic equivalent of a scavenger hunt. Find the one new point of light hiding among thousands of old stars, background galaxies, instrumental glitches, and false alarms. The first hours after the alert was chaos in the best way possible. Teams around the world pulled up catalogs of known galaxies inside the distance range inferred from the gravitational wave signal, about 140 million light-years or give or take. They prioritized nearby, relatively bright galaxies in the triangulated sky region and started sweeping them, systematically comparing fresh images to archival ones. Most frames looked exactly the same smudges, the same stellar speckles, nothing obviously new. But then, about 11 hours after the merger, the 1-meter SWOPE telescope in Chile imaged a lenticular galaxy called NGC 4993 and spotted something that wasn't there before: a new, star-like point of light just off to one side of the galaxy center. That transient was quickly labeled SSS-17A and then AT2017 GFO in the official naming scheme. Crucially, it was the only new object in the right region and at the right brightness to match the gravitational wave distance. Among all the galaxies in that messy localization patch, this was the one place that had genuinely changed. From that moment on, AT2017 GFO became the most intensively stalked dot of light in modern astronomy. In the first day, its color told a surprising story. It was distinctly blue, quite bright in optical bands. That blue phase looked more like a hot, smooth black body radiator than a line-filled spectrum of a classic supernova. Over the next couple of days, the transformation was dramatic enough that you could show it in a time-lapse. The blue light faded quickly. The source reddened and became progressively brighter in the infrared relative to the optical. By the end of the first week, most of the action had shifted out of the visible range altogether, with infrared instruments picking up the fading glow, while optical telescopes saw little more than a ghost of the original flash. That color evolution was exactly what kilonova theorists had been predicting for years. The early blue emission hinted at a component of ejecta that was relatively poor in the heaviest line-blocking elements, lanthanides and friends. Such material stays more transparent in the optical, so it can shine blue while it's still hot. The later red and infrared dominance pointed to a second, heavier component of ejecta loaded with lanthanides and other R-process products. Those elements have incredibly complex electron structures that produce forests of absorption lines, especially in the blue and ultraviolet, effectively trapping shorter wavelength photons and re-emitting the energy at longer wavelengths. In other words, as the ejecta expanded and cooled, the blue light got suppressed by all those heavy element opacities, and the thermal glow slid into red and infrared bands. Watching AT 2017 GFO go from hot blue spark to smoldering red ember in a matter of days was like watching a simulation come to life. Of course, astronomers weren't content to just marvel at the color. They treated the light curves of AT 2017 GFO, measurements of its brightness over time and different filters, as data to be interrogated. By fitting those multi-band light curves with models of radioactive heating and radiative transfer, they could estimate how much mass had been ejected and how much energy was coming from radioactive decay. The numbers were jaw-dropping. The preferred models pointed to at least about 0.05 solar masses of R-process-rich ejecta. 0.05 suns doesn't sound like much until you translate it. That's roughly 16,000 Earth masses of heavy stuff, including on the order of 10 Earth masses worth of gold and platinum combined. One event, one merger, had manufactured enough precious metals to make every jewelry store on Earth look like a dusty trinket stand. What made AT 2017 GFO more than just a pretty transient was the sheer coverage it got. Over 70 observatories across the electromagnetic spectrum piled on. Optical and infrared telescopes tracked the color evolution. X-ray and radio observatories watched the longer-term afterglow from relativistic jets plowing into surrounding material. Spectrographs captured the broad blended absorption features that hinted at the presence of heavy elements, even if we couldn't pick out individual lines neatly yet. For the first time, a single astrophysical event had a complete multi-messenger profile, gravitational waves giving us the in-spiral and masses, gamma rays announcing the ultra-relativistic jet, optical and infrared light showing the radioactive kilonova, and later X-rays and radio filling in the environment and jet structure. That's why people say multi-messenger astronomy was born with JWST and AT 2017 GFO. We'd had hints before. Neutrinos from a supernova here, gamma rays plus optical afterglows from gamma ray bursts there, but never a case where gravitational waves and electromagnetic light marched so clearly in lockstep from the same source. Science magazine named it Breakthrough of the Year in 2017, not just because it was cool, it was, but because it proved a new way of doing astronomy, no longer relying on one kind of signal at a time, but stitching together a coherent story from space-time wiggles, high-energy flashes, and slowly fading glows. And woven through that story was the periodic table. For decades, astronomers, nuclear physicists, and cosmologists had argued about where roughly half of the elements heavier than iron came from. Some models made exotic supernovas the heroes, others preferred accretion disks around newborn black holes. Neutron star mergers and kilonovae had their champions, but without a clean example, it was all speculative horse trading. AT 2017 GFO changed the tone. Its light curves and spectra weren't just consistent with our process material, they practically screamed it. The amount of ejecta, the timescales, the colors, all lined up with the idea that neutron star mergers can be prolific factories of heavy elements. When you fold events like this into models of galactic chemical evolution, you find that a reasonable rate of such mergers over billions of years can account for much of the universe's gold, platinum, europium, and other R-process elements. So in a sense, the night the sky lit up over NGC 4993 wasn't just a random fireworks display in a distant galaxy. It was the universe finally answering a long-standing question with a single luminous gesture. Where do many of the heaviest elements come from? Here, right here in the radioactive embers of merging neutron stars. One rare precious kilonova, caught in exquisite detail, was enough to redraw the lines on the periodic table's family tree and move neutron star merger from the maybe column to the main suspects for some of the most coveted atoms we know. By the time AT 2017 GFO faded from the sky, We weren't just staring at a pretty light curve. We were watching a nuclear assembly line in action. All that talk about 16,000 Earth masses of heavy elements needs a translation layer. How did a blob of shredded neutron star matter turn into gold, platinum, uranium, and all the other heavyweight members of the periodic table? The answer is simultaneously simple and wild. The R process, or rapid neutron capture, which is basically nature's way of speed-running nuclear Lego. Here's the R process in one breath. Take a nucleus, say some isotope of iron, and dump it into a soup with an absurd density of free neutrons. If the neutron density and temperature are high enough, that nucleus will start grabbing neutrons way faster than it has time to decay. Each capture makes it heavier. Add one neutron, then another, climbing to ever higher mass numbers. Eventually, you end up with a ridiculously neutron-rich, unstable nucleus that says nope and beta decays. One of its neutrons turns into a proton, an electron, and a neutrino. The neutrino flies off, the electron is emitted, the proton stays, bumping the element one step up the periodic table. Rinse and repeat. Neutron captures push you up and to the right on the chart of nuclides. Beta decays walk you diagonally back towards stability. That dance is how you build elements like gold, platinum, and uranium. They are, quite literally, leftovers from a neutron capture feeding frenzy that eventually calmed down. The tricky part is that you can't run the R process just anywhere. You need a ridiculous supply of free neutrons, high enough temperatures to keep things reactive, and conditions that last long enough for nuclei to climb the ladder before everything disperses. For a long time, theorists pointed to a few candidate environments: the neutrino-driven winds in core collapse supernova, jets from collapsars, massive stars collapsing into black holes with accretion disks, and lurking on the sidelines, the debris from neutron star mergers. Neutron star matter is basically a giant vat of neutrons to begin with, so if you can decompress even a small fraction of it and let it expand, you automatically get the right kind of neutron-rich environment. The question was never, can the R process run there? But does this happen often enough and with enough ejecta to match what we see in real stars?
Neutron star mergers have a few unfair advantages in this game. First, the ejecta are born neutron-rich by construction. You're ripping matter straight out of objects whose entire identity is, I'm overwhelmingly neutrons. Second, the densities and temperatures during and just after the merger are perfect for R process conditions. Hot enough to keep nuclei from freezing out instantly, dense enough in neutrons that capture timescales are shorter than decay timescales. Third, the ejecta come in multiple flavors: fast tidal tails, disk winds, possible polar outflows, with slightly different neutron richness, giving you a natural way to populate different parts of the heavy element abundance pattern. Simulations run years before JWST already show that if you take a realistic merger, toss out on the order of 0.01 to 0.05 solar masses of ejecta, and let the R process go wild, you can reproduce a lot of the observed features of R process elements in old stars. What AT 2017 GFO did was remove the word if. Before that event, neutron star mergers were very compelling PowerPoint slides. After it, they were a watched experiment. Early optical spectra of AT 2017 GFO looked almost boring: smooth curves, not many sharp features, consistent with a hot, quasi-blackbody emitter and an atmosphere without dramatic line imprints. But as days passed, the spectra started to grow broad, smeared-out absorption features. Not crisp fingerprints from individual elements, but the kind of messy, blended pattern you expect when you have a forest of atomic transitions from heavy, complex ions, especially lanthanides, the rare earth elements with crowded electron shells. Lanthanides are R process poster children. They're produced almost exclusively in rapid neutron capture environments, and they have insane opacities in the blue and ultraviolet. They soak up shorter wavelength photons and re-radiate the energy at longer wavelengths. That's exactly the behavior the light curve was showing. Blue light suppressed over time, infrared taking over. The detailed spectral models are still messy. Heavy elements have absurdly complicated atomic structures, and lab data are incomplete. But the overall match between what lanthanide-rich ejecta should look like and what AT 2017 GFO actually looked like is very hard to ignore. The universe wasn't just hinting. It was flexing its rare Earth collection directly at us. Once you trust the models enough to interpret the light curves, you can play the accounting game. Take a typical neutron star merger ejecting about 0.05 solar masses of our process-dominated material. Sprinkle those events through a galaxy's history at a rate consistent with what gravitational wave detectors and binary pulsar populations suggest, roughly 1 per 10,000 to 10,005 years in a Milky Way-like galaxy. Integrate over billions of years. The total mass of our process elements you get is of the same order as what's inferred from stellar abundance measurements in the real Milky Way. In other words, if neutron star mergers like JW170817 have been happening at a modest but steady rate over cosmic time, they can plausibly account for the galaxy's budget of many heavy elements. That brings a story disturbingly close to home. The gold in a wedding ring, the platinum in a lab catalyst, the europium lines astronomers see in the spectra of old halo stars. Those atoms were almost certainly not just from some generic supernova. Their genealogy traces back to one or more R-process events, very likely including neutron star mergers. Somewhere in the history of the Milky Way, there were kilonovae that no one saw, going off in the quiet outskirts of the galaxy, dumping clouds of freshly minted heavy atoms into space. Those clouds got stirred into star-forming gas, folded into the birth environments of new stars, and eventually condensed into planets and crustaors. When you hold a piece of gold, you're holding the cooled ashes of one of the rarest astrophysical factories we know. The twist is that for a long time, we gave credit elsewhere. Older models leaned heavily on certain flavors of supernova, especially exotic, strongly magnetized or rapidly rotating core collapses as the main R-process sites. Those might still contribute, and there are hints from some extremely metal-poor stars that an additional very early R-process channel might be needed in some environments. But the kilonova data from JW170817 made it clear that supernovae cannot be the whole story. They just don't produce enough of the right stuff, often enough with the right abundance patterns to match everything we see. Kilonovae forced a rebalancing. They don't have to own 100% of the R-process budget to be crucial. Even if some collapsed stars or weird supernovae chip in, neutron star mergers now sit at center stage. The universe had been hiding its real heavy element foundries, not in the big obvious explosions we'd gotten used to, but in these ultra-rare, easily missed collisions of dead stars. We were looking at the fireworks and assuming that's where the gold came from. All along, the true factories were tiny, fast, and mostly invisible, except for the one time we caught one in the act and finally connected the glitter on our fingers to the physics of rapid neutron capture in a fading red smudge 140 million light-years away. If kilonovae are the secret factories where the universe forges gold, then gamma-ray bursts are the moment those factories accidentally fire a cosmic nail gun across the universe. When two neutron stars merge, they don't just puff out a gentle radioactive cloud. Under the right conditions, they can also launch ultra-relativistic jets, narrow beams of particles and radiation moving so close to the speed of light that fast doesn't really do it justice. When those jets are pointed even vaguely in our direction, we see them as gamma-ray bursts, brief, intense flashes of high-energy photons that for a few seconds can outshine entire galaxies. Astronomers have been obsessed with GRBs since the Cold War, when military satellites meant to spot nuclear tests started seeing mysterious flashes coming from deep space instead of Earth. Over time, a pattern emerged. Gamma-ray bursts come in two main flavors. Long GRBs, lasting more than about 2 seconds, are usually tied to the deaths of massive stars, core collapse events that produce collapsing stellar cores, black holes, and energetic jets punching their way out of the star's envelope. Short GRBs, under 2 seconds, have long been suspected to come from compact object mergers, neutron star, or neutron star black hole collisions. The durations, the host galaxies, and the lack of supernovae for short bursts all lined up with that idea, but for years it was circumstantial. We had the crime scene and a decent motive, but no security camera footage. JW170817 changed that. When LIGO and Virgo recorded the 100-second chirp of a binary neutron star in spiral, and then, 1.7 seconds later, Fermi and Integral saw a 2-second gamma-ray flash, GRB 170817A, from the same region of sky, the missing link finally snapped into place. A neutron star merger had produced a short GRB. That one pairing nailed down what decades of hints had been pointing toward. At least some short GRBs really are the death screams of merging neutron stars, often accompanied by a kilonova as the slower, more isotropic ejecta glow and decay. But the universe had already given us an almost confession a few years earlier, in the form of GRB 130303b. This was a short GRB, about 0.2 seconds long in gamma rays, detected in 2013. Follow-up observations with the Hubble Space Telescope found something odd in the infrared, an extra red component in the afterglow, about 9 and 30 days after the burst. It was fainter and redder than expected from a standard GRB afterglow alone, and matched predictions for a kilonova-like component. Many people took this as the first solid evidence that at least some short GRBs had kilonova partners, that neutron star mergers were indeed happening and leaving behind radioactive embers. But without gravitational wave confirmation, skeptics could still say, maybe this is just a weird jet-environment interaction. GRB 130303b was the almost first kilonova, compelling, but not quite courtroom-proof. GW 170817A, on the other hand, was weird in the opposite direction. Given that it was so close by cosmic standards, 140 million light-years is right next door for GRBs. You'd expect it to be blazingly bright in gamma rays if we were looking straight down the barrel of the jet. Instead, it was surprisingly faint, almost underwhelming compared to typical short GRBs seen at much larger distances. The best explanation is geometric. We didn't catch the jet head-on. Models suggest we saw it about 30 degrees off-axis, meaning we were looking at the structured wings of the jet, not the blinding core. In a relativistic jet, most of the emission is beamed tightly into a cone along the motion direction. Viewed from the side, you get a wimpy-looking burst and a different afterglow evolution. The faintness of GRB 170817A combined with the later radio and X-ray data gave us a huge clue about jet structure and beaming angles. These jets aren't simple top-hat beams. They have structured energy profiles with a bright core and fainter wings. This off-axis view turned out to be a gift in disguise. If most neutron star mergers launch such structured jets, and only a tiny fraction are pointed directly at us, then the GRBs we see are just the tip of an iceberg. For every short GRB we detect, there could be dozens or hundreds of neutron star mergers whose jets are pointed elsewhere, still making kilonovae and heavy elements, but never lighting up our gamma ray detectors. Kilonovae thus become a way to find the quiet mergers, the ones whose jets miss us, but whose radioactive debris still glows in optical and infrared light. Just when you think you've got the taxonomy straight, long GRBs are massive star collapses, short GRBs are mergers, kilonovae were supposed to quietly attach themselves only to the short side, like a neat little label. Instead, as we attach kilonova signatures to events of various durations, it's becoming clear that there's a continuum of behaviors. Some explosions we used to confidently blame on collapsing massive stars might actually hide a merger origin. Some may involve more complex central engines that blur the line between star death and compact object chaos. GRB 211211A, for example, hung around in gamma rays longer than you'd expect from a textbook short burst, but its host environment and follow-up data argue strongly for a compact object merger origin rather than a massive star dying. GRB 230303A went even further. JWST's infrared spectra revealed signatures consistent with heavy element production, making it one of the best kilonova candidates since AT 2017 GFO, despite its long gamma ray duration. These oddballs blur the nice clean line we drew at 2 seconds and say, actually, reality is squishier than your categories. Some mergers can produce longish bursts if the jet or engine behaves differently. Some collapsars can produce shortish spikes. Nature did not read our classification papers. The big picture consequence is that even our gamma ray taxonomy is starting to crack. The old story was simple: long GRBs, dying giant stars; short GRBs, compact mergers. Kilonovae were supposed to quietly attach themselves only to the short side, like a neat little label. Instead, as we attach kilonova signatures to events of various durations, it's becoming clear that there's a continuum of behaviors. Some explosions we used to confidently blame on collapsing massive stars might actually hide a merger origin. Some may involve more complex central engines that blur the line between star death and compact object chaos.
Kilonovae are the troublemakers here, in the best way. They're giving us an independent tag,
This event produced a pile of R-process ejecta, regardless of how long the gamma-ray fireworks lasted. Once you have that tag, you start noticing that the neat 2-bin division of GRBs is more of an approximate guideline. The universe, it turns out, organizes its most violent explosions the way humans organize their music playlists. Genres are useful, but every so often you get something that's half one thing, half another, and then your categories start to look more like suggestions than laws. When AT 2017 GFO finally gave us a kilonova in full 4K, it didn't just confirm our theories, it marched right up to them and started poking holes. Before 2017, merger simulations were like confident concept art, dramatic, colorful, and based on decent physics, but full of assumptions about neutrinos, magnetic fields, and geometry. Then the universe dropped a real data set on our desks, and in classic QA fashion, it came with the long list of, "This doesn't quite match what you drew." The first big bug report was the blue versus red puzzle. In the very first day or so, AT 2017 GFO was surprisingly blue and bright in optical bands. That screams fast, relatively lanthanide-poor ejecta, material with fewer of the super opaque heavy elements, moving quickly and radiating almost like a hot, smooth photosphere. A few days later, the color evolution flipped. The blue light dropped off a cliff and red/infrared emission took over, which is exactly what you'd expect from slower, lanthanide-rich ejecta where heavy elements choke off short wavelength photons and re-emit at longer wavelengths. So the data were basically telling us, you don't just have one blob of ejecta, you have at least two. A blue, fast, lanthanide-poor component and a red, slower, lanthanide-rich one. Pre-2017 simulations did predict multiple components, but many didn't give the blue part enough love. The common picture was tidal tails sling out very neutron-rich, lanthanide-heavy debris in the equatorial plane, good for red, and maybe you get some slightly less neutron-rich stuff from winds off the accretion disk, potentially bluer. But the amount of blue ejecta AT 2017 GFO seemed to require to match its early brightness and color was higher than many models comfortably produced. That pushed theorists back to their code, tweaking the neutrino physics because neutrino irradiation can rave the electron fraction in the outflows, making them less neutron-rich, and rethinking disk winds, magnetically driven outflows, and the 3D geometry. The data were effectively saying, whatever you thought your disk and remnant were doing, they're doing more of the make lanthanide poor stuff and throw it out fast part. Then there was the sheer quantity and speed of the ejecta. The light curves of AT 2017 GFO, when fed through radiative transfer models, pointed toward a total ejecta mass of around 0.05 solar masses, with chunks of it moving at 0.2 to 0.3 times the speed of light. That's a lot of matter and a lot of kinetic energy to get rid of in a brief, violent moment. Some merger simulations, especially the ones where the merged remnant promptly collapses into a black hole, tended to produce less ejecta, closer to the 0.01 solar mass range, and sometimes slower. To get 0.05 solar masses out, you either need more efficient tidal stripping, more robust disk winds, or a remnant that hangs around as a hypermassive neutron star for a bit before collapsing, giving it time to pump energy and matter into the surrounding disk. So the tension became, did GW170817's remnant survive as a rapidly rotating, temporarily supported neutron star for tens to hundreds of milliseconds, maybe even longer, before collapsing? If it collapsed too quickly, some models struggled to make enough ejecta to match the kilonova luminosity. If it lived too long, other observables like the GRB and late-time emission could be overpowered by a magnetar-like central engine. The kilonova's brightness effectively turned into a timer on how long the remnant could cheat death before gravity finished the job. Geometry added another wrinkle. Naively, you'd expect merger ejecta to be somewhat flattened or directional. Tidal tails in the orbital plane, disk winds with preferred directions, jets blasting along the poles. Early time observations of AT 2017 GFO's thermal components, though, suggested something surprisingly close to spherical symmetry, at least for the main glowing blob. The light curves and approximate blackbody fits didn't scream highly asymmetric. That doesn't mean the ejecta were perfectly spherical, reality is rarely that kind, but it did suggest that there was a substantial quasi-isotropic outflow component. Again, theorists had to go back to the drawing board.
Maybe the hypermassive remnant launched more spherical winds, or magnetic turbulence in the disk puffed things out more evenly than expected. The universe was saying, your nice clean donut diagrams are cute, but the real thing is more like a messy puffball. And then there was the afterglow that refused to behave like a simple one-and-done event. Long after the optical and infrared kilonova had faded from view, X-ray and radio telescopes kept watching the position of AT 2017 GFO. Over months, then years, the X-ray emission evolved in a way that pointed to a structured jet plowing into the surrounding medium. Instead of a quick rise and decay, the afterglow brightened on slower timescales, consistent with us seeing the edge of an off-axis jet, plus possibly some slower-moving, mildly relativistic cocoon of material around it. Even years later, Chandra was still picking up X-rays from the site, forcing more nuanced models that include angular structure, energy injection, and interaction between the jet and merger ejecta. The system refused to be done on the tidy schedule our simplest models had penciled in. All of this together turned AT 2017 GFO into less of a victory lap and more of a bug tracking dashboard. Every odd feature in the light curves, the rapid color change, the overall brightness, the time evolution of different bands, became a constraint. Every mismatch between simulation and observation was a to-do item. Adjust the equation of state, retune the neutrino transport, refine the disk wind prescriptions, account for 3D structure and viewing angle. Codes that looked perfectly respectable on synthetic data suddenly had to face a real messy universe and admit, right, okay, we were missing a few things. That's the deeper stake here. Kilonovae like AT 2017 GFO aren't just confirming known physics, they're stress testing our entire machinery for simulating extreme matter and strong gravity. When your model's light curve is too red, nature is telling you something about the composition of the ejecta and the microphysics of neutrino interactions. When it's too dim, it's scolding your assumptions about how much mass can be thrown off and how long the remnant survives. When the geometry doesn't match, it's highlighting where your 3D magnetohydrodynamics is too simplified. AT 2017 GFO was in a sense a giant cosmic bug report filed against our best merger simulations. And unlike normal software, you don't get to rerun the universe with different parameters. You get one event, one set of logs, and the challenge of updating your mental firmware to match.
For all the drama we've squeezed out of kilonovae so far, there's a deeply funny fact lurking underneath. In the gold standard category, we basically have one event where we heard the gravitational waves, saw the gamma rays, tracked the optical and infrared light from hours to weeks, and watched the afterglow unfold in X-rays and radio. JW170817, AT 2017 GFO, is still the only kilonova with that kind of pristine multi-messenger fingerprint. Everything else is a spectrum of probably, maybe, and could be, but there are other candidates. Some short gamma ray bursts like GRB 130303b and GRB 230307a show extra red or infrared light that looks a lot like what we'd expect from a kilonova layered on top of the usual jet afterglow. A few long-duration oddballs also seem to have kilonova-like components hiding in their late-time emission. These are incredibly valuable, but they're missing one or more key pieces. No gravitational wave detection, patchy time coverage, noisy host environments, or incomplete spectra. Compared to GW170817, AT 2017 GFO, they're like crime scenes where you've got a weird footprint and a blurry camera frame instead of high-res video plus fingerprints plus a signed confession. Meanwhile, the sky surveys that should be our kilonova hunting workhorses are constantly getting catfished. Teams have started running dedicated searches, often using facilities like Pan-STARRS, to look for fast, faint, rapidly evolving transients that might be kilonovae without a known GRB or gravitational wave trigger. On paper, this sounds easy. Tell the algorithm to find things that brighten and fade in a few days, skew red, and don't look like normal supernovae. In practice, the universe is full of chaotic nonsense that fits that description. Stellar eruptions from massive, unstable stars like luminous blue variables, weird outbursts from interacting binaries, flares near active galactic nucleo, all of these can masquerade as kilonova-like in early data. So survey teams flag a bunch of promising candidates, point bigger telescopes at them, get more detailed light curves and spectra, and one by one, the candidates fall apart under scrutiny. Recent Pan-STARRS-based work literally went through a list of fast red transients that had been touted as kilonova possibilities and systematically demoted them to other more mundane classes. 11 maybes in, 0 actual kilonovae left standing. The universe keeps handing us cosplay, not the real thing. So if we almost never see these events, how do we get any numbers out at all? That's where the gravitational wave detectors quietly carry the whole statistics department on their backs. LIGO, Virgo, and Cogra catalog not just detections like JWST 0817, but also stretches of observing time where they didn't see binary neutron star mergers. From the combination, we saw X in this much time and didn't see Y, you can estimate merger rates. How many binary neutron star coalescences happen per unit volume per unit time in the universe? Those estimates come with hilariously wide error bars, but they give a ballpark. Something like tens to maybe a few thousand binary neutron star mergers per cubic gigaparsec per year. A cubic gigaparsec is a huge volume, containing many thousands of Milky Way-sized galaxies. Even if you take the high end of that range, when you scale down to a single galaxy like ours, you're still looking at a good luminous kilonova maybe once in 10 to the 4th to 10 to the 5th years. On human timescales, that's basically never. On galactic timescales, it's occasionally, but don't blink. And that's before you fold in the selection effects. To show up as a short gamma-ray burst, the merger has to launch a jet that's pointed roughly in our direction. Most won't be. To be caught as a kilonova in optical surveys, it has to be close enough, bright enough, and happen in a part of the sky and at a time when we're actually looking with the right cadence and filters. The blue phase dies in a day or two. The red phase might peak in the infrared where ground-based surveys are weak. Clouds, daylight, the moon, telescope schedules, mundane annoyances eat into our effective sensitivity. The upshot is, the universe might be making far more kilonovae than we currently see, but our observational neck has big, obvious holes right where these things like to slip through. So we end up in this absurd situation. We're revising the heavy element origin story for the entire galaxy, constraining the equation of state of neutron star matter, and even weighing in on the cosmic expansion rate, all with one textbook event and a handful of sketchy cousins. In any other field, basing huge theoretical shifts on a sample size of 1 would get your proposal laughed out of the room. In astrophysics, sometimes that's just the game. The universe gives you one beautifully instrumented once-in-a-century experiment and a bunch of tantalizing near misses and says, make the most of it. The saving grace is that the rarity is mostly on our side of the equation, not nature's. The universe is huge, time is long, and neutron star binaries are out there spiraling toward doom whether we're listening or not. From the universe's perspective, kilonovae are uncommon, but not mythical. They happen. The bottleneck is our technology and our cadence. Our lasers aren't yet sensitive enough, our wide-field cameras aren't yet fast and deep enough, our automated classification isn't yet smart enough. As those improve, the sample size will eventually start to crawl upward from 1 to a few to dozens. But right now, we're in a uniquely precarious and exciting moment. Almost everything you've heard in this story about kilonovae rates, yields, geometry, and the role in creating your gold is anchored to one exquisitely observed cosmic lab experiment, plus a shadowy supporting cast. We are, in a very literal sense, trying to understand the universe's rarest explosions from essentially one smoking crater and a rumor mill. And somehow, that's still been enough to start rewriting the periodic table's backstory. Once the glare of a kilonova fades, we're left with an oddly intimate question about something 140 million light-years away. So, what's actually sitting in the middle now? After all that drama, the in-spiral, the chirp, the gamma-ray flash, the radioactive glow, the universe quietly moves on. But for physicists, the end state of JWST 0817 is where things get really existential. Did those two neutron stars fuse into a new ultramassive neutron star that somehow survived? Did it briefly exist and then collapse? Or did gravity go straight for the full upgrade and give us a baby black hole almost immediately? Gravitational wave data give us the first clue. From the chirp of JWST 0817, we know the total mass of the binary system was about 2.7 to 2.8 times the mass of the Sun. That's already close to or above the maximum mass a neutron star can support if it's not spinning too fast, the TOV limit we talked about earlier, somewhere around 2.0 to 2.2 solar masses. But right after the merger, the remnant isn't cold and quiet. It's hot, rapidly rotating, and supported not just by degeneracy pressure and nuclear forces, but also by differential rotation and thermal pressure. For a brief time, that extra support lets it exist as a hypermassive neutron star, a ridiculously heavy, swollen, unstable object that's basically on borrowed time. Most models for JWST say that's exactly what happened. The remnant lived as a hypermassive neutron star for at most a fraction of a second, to maybe a second or so, before collapsing into a black hole. That's long enough to stir up the surrounding matter, launch winds, and help produce some of the ejecta we see as the kilonova, but not long enough to act like a persistent energy engine for days. If it had survived as a stable or even long-lived metastable neutron star, its rapid rotation and ultra-strong magnetic fields could have pumped a lot more energy into the ejecta than we actually observe. The kilonova would likely have been much brighter, bluer for longer, or otherwise visibly jacked up by a central engine. This leads straight into the magnetar hypothesis, which is exactly what it sounds like. Maybe the merger left behind a highly magnetized, rapidly spinning neutron star, a magnetar, that dumped extra energy into the surroundings. Some models invoke such a magnetar remnant to explain certain bumps and features in the light curves of kilonova candidates. Extra luminosity at late times, unusual color evolution, or extended X-ray emission. It's an attractive idea because magnetars are absurdly good at turning rotational energy into electromagnetic power. But the data from JW170817/AT2017 GFO push back. If a magnetar with enough energy had hung around for hours or days, it would probably have over-energized the ejecta, making the kilonova too bright compared to what we actually saw. The light curves and spectra look more like what you'd expect from ejecta powered primarily by radioactive decay, maybe with the short-lived remnant helping shape the early outflows, rather than from a long-lived magnetar dumping serious energy over extended timescales. So theorists are split. Some subtle features might hint at a slightly longer-lived remnant than instant collapse, but the kilonova definitely doesn't look like it had a central lighthouse blazing away for days. Hidden inside this argument is a quiet but powerful constraint on the neutron star equation of state, the way matter behaves at ridiculous densities. If the remnant of JW170817 could have remained a stable neutron star, that would imply neutron star matter can support a non-rotating mass above about 2.7 solar masses, which would mean an extremely stiff equation of state. But we don't see strong evidence for such a long-lived remnant. The absence of clear magnetar-like signatures, plus modeling of the ejecta and gravitational wave signal, suggests that a star that massive couldn't stay a neutron star for long. It had to collapse. That in turn rules out some of the stiffest proposed equations of state, those that predict supermassive neutron stars that are too robust against collapse. In one stroke, JW170817 chopped off a chunk of parameter space for what matter can do at nuclear and supernuclear densities. Of course, not every compact binary merger will follow the same script. Some will involve a neutron star orbiting a black hole instead of another neutron star. Those mergers are a different beast entirely when it comes to kilonovae. If the black hole is too massive or not spinning fast enough, it can swallow the neutron star whole in one gulp with relatively little tidal disruption. In that case, hardly any neutron-rich matter gets tossed out into space, which means hardly any ejecta and no bright kilonova. You'd still get a gravitational wave signal from the inspiral and merger, but the electromagnetic sky would stay mostly dark. Events like GW230529, likely a neutron star merging with a low-mass black hole, hint at exactly this kind of diversity. Some such systems might shred the neutron star outside the black hole horizon, creating a kilonova-like outburst. Others might simply gulp it down, leaving only gravitational waves as evidence. From the standpoint of how much gold do you make, those details matter a lot. Not all mergers are equally generous. Some are element factories, others are stingy. And that's the bigger philosophical punch. When we ask, did this merger make a neutron star, a magnetar, or a baby black hole? We're really asking, what does matter do when you push it past every limit we can probe on Earth? The identity of the remnant is a verdict on the equation of state. A universe in which hypermassive, long-lived magnetars are common after mergers is a universe where nuclear matter is more resilient than we thought. A universe where remnants collapse almost immediately is one where gravity steamrolls even the strongest known forces as soon as it can. Kilonovae make these verdicts visible. They are one-shot experiments. Gravity and nuclear physics build an object at the edge of stability, slam it, and let us watch the debris. How bright the kilonova gets, how its colors evolve, and whether there's lingering X-ray or radio emission all feed back into that central question. Somewhere in those fading photons is the answer to neutron star or black hole. And woven into that answer is a deeper one. What can matter be when almost nothing can hold it up anymore? By now, JWST is doing an almost obnoxious amount of work for us, testing nuclear physics, exposing our process factories, and revealing jet geometry. But the universe wasn't done squeezing meaning out of that one bang. It also handed cosmologists a new toy for measuring how fast space itself is stretching. The same event that forged gold and platinum also joined the fight over one of the biggest arguments in modern cosmology: how fast is the universe actually expanding? Traditionally, we've measured the cosmic expansion rate using standard candles. These are objects whose true luminosity, the amount of energy they emit per second, is either known or can be calibrated. Type A supernovae are the classic example. Their peak brightness correlates with how quickly they fade, and that relation can be calibrated using nearer objects whose distances we know by more geometric methods, like parallax or Cepheid variables. Once you know how bright a supernova should be, you compare that to how bright it looks, and using the inverse square law, infer its distance. Measure the redshift of its host galaxy, how stretched its light is by the expansion of the universe, plot distance versus redshift for lots of supernovae, and you extract the Hubble constant, h0, the expansion rate in kilometers per second per megaparsec. That whole chain of methods is called the cosmic distance ladder, and it's both ingenious and somewhat fragile because each rung depends on calibrations from the one below. Gravitational wave sources offer a very different kind of yardstick, standard sirens. Instead of relying on intrinsic brightness, we rely on the physics of the waveform. When two compact objects spiral together, general relativity tells us exactly how the amplitude and frequency evolution of the gravitational waves depend on their masses and on how far away they are. The farther they are, the weaker the signal. The closer, the stronger. By fitting the waveform, you can estimate a luminosity distance directly, no intermediate ladder required. It's like hearing a familiar siren and deducing how far the ambulance is by how loud it is and how its pitch changes as it passes. Except the ambulance here is two neutron stars, and the air is space-time. JW1708117 was the first time we could play this game in full. From the gravitational wave signal alone, the LIGO Virgo team derived the distance to the source of around 40 megaparsecs, with substantial uncertainties due to degeneracies, e.g., between distance and inclination angle. That gives you this thing is about X million light years away, but not yet a Hubble constant, because you still need the corresponding redshift, how much the universe has stretched during the journey of that signal. That's where the kilonova comes in. Because AT 2017 GFO was localized to NGC 4993, we could measure the redshift of that specific galaxy with ordinary spectroscopy. Now you've got both pieces, a distance from gravitational waves and a redshift from light. Put distance on one axis, redshift on the other, and even with a single point, plus an assumed local peculiar velocity correction, you can sketch out an estimate of HO. Early analyses from JW1708117 alone landed in the awkward middle ground between the two warring camps, the higher HO values inferred from local supernova measurements, and the lower HO values inferred from the cosmic microwave background by Planck. The error bars were huge, but the mere fact that a single neutron star merger could land roughly in the gap made people sit up. Standard sirens suddenly weren't just a cute idea. They were a third referee entering the ring. The magic really hinges on that little fading smudge of a kilonova. Without the optical counterpart, JW1708117 would be just a gravitational wave event with an estimated distance. Useful, but cosmologically incomplete. Distances alone don't tell you how fast the universe is expanding unless you know the redshift of the source. You could guess a redshift statistically by looking at all galaxies in the localization volume, but the uncertainty would balloon. AT 2017 GFO turned a 3D cloud of possibilities into a single concrete host, NGC 4993, with a well-measured redshift. That anchored the standard siren distance in real cosmic coordinates. The kilonova didn't just show us heavy elements, it supplied the missing half of the distance redshift pair. Now imagine scaling this up. One event gives a hilariously noisy measurement of HO. 10 well-measured events, each with a clean gravitational wave distance and a confidently identified host galaxy, start to give something competitive with other methods. A few dozen, spanning different parts of the sky and different distances, and you have an independent probe of the expansion rate that doesn't care about C-feeds, supernova calibrations, or the detailed physics of the early universe encoded in the cosmic microwave background. Standard sirens plus kilonovae offer a way to triangulate reality between those other methods. If they side with the supernovae, that's one story. If they side with Planck, that's another. If they land somewhere else entirely, then the HO tension stops being a matter of who calibrated what wrong and starts to being a big red flag for new physics. Maybe in dark energy, maybe in gravity, maybe in something we haven't named yet. So now whenever a new neutron star merger pops off in the universe, it's not just a question of did it make gold, it's did we catch the chirp and did we find the counterpart? Because each clean kilonova plus GW combo doesn't just enrich the periodic table, it tightens the screws on cosmology. Rare as they are, these explosions have muscled their way into the front lines of precision measurements. One extremely unlikely stellar car crash in a distant galaxy is now part of an argument about whether our standard model of cosmology is missing crucial pieces. A kilonova was already bizarre for turning dead stars into jewelry. The twist is that the same event also doubles as a cosmic ruler, quietly helping us check whether the entire universe is expanding the way our equations say it should. That little blue then red blur in NGC 4993 isn't just a relic of nuclear violence, it's a tick mark on the great yardstick of spacetime. The funny thing about kilonovae is that they're loud in all the hardest ways to notice. They shout for a few days in colors we're bad at watching, then go quiet forever. They're faint compared to supernovae, they evolve fast compared to normal transients, and most of them are happening at distances where even a big telescope has to squint. For decades, our sky surveys were basically designed for the opposite kind of object: slow, bright, patient explosions. If you only look at a patch of sky every 3 or 4 nights, the blue phase of a kilonova can flare, peak, and already be sliding away toward the red by the time you wander past again. By the next visit, you're staring at a faint red smudge you can barely distinguish from background noise. It's like trying to study lightning with a weekly weather report. That's why so much hope is riding on the Vera C's Rubin Observatory and its Legacy Survey of Space and Time, LSST. Rubin is essentially a machine built to not blink. Once it comes fully online, it will scan the entire visible sky every few nights with deep white field images, generating a torrent of transient alerts, millions of something changed to your pings per night. Buried in that fire hose will be exactly the kind of light curves kilonovae produce. Things that rise and fade on dayish timescales, shift color rapidly, and don't behave like standard supernovae. Rubin's trick isn't just seeing them, it's flagging the weirdos in real time, so other telescopes can pounce while the blue phase is still alive and the geometry and composition clues are freshest.
Of course, wide field surveys are only half the story. You also need telescopes that can zoom in and dissect the light, especially in the infrared where the red lanthanide-rich kilonova components glow brightest. This is where space observatories like JWST are already earning their keep. JWST has started taking mid-infrared spectra of promising candidates, like the kilonova associated with GRB 230307A, revealing broad, heavy element features that ground-based telescopes can't easily access through Earth's atmosphere. In the near future, the Nancy Grace Roman Space Telescope will join the party, with wide-field infrared imaging and spectroscopy that's perfect for catching and following up late-time kilonova emission on larger patches of sky. Rubin can scream, "Hey, something weird and fast just happened over here," and Roman or JWST can reply, "Cool, let's see what atoms are actually glowing in that mess." Because humans are chronically outnumbered by data, we're also throwing algorithms at the problem. Teams are building machine learning pipelines specifically trained to spot kilonova-like behavior in the ocean of transients Rubin and other surveys will detect.
the pattern they're hunting is subtle: a fast rise in decay, rapid reddening, and absolute luminosities in a particular range. The catch is that the universe happily produces lots of other nonsense that can fake that pattern. Peculiar supernovas, flaring active galactic nuclei, eruptions from luminous blue variables, dusty outbursts, and star-forming regions. Recent work has shown just how hard it is to avoid contamination by these imposters. Networks that look great in training can get blindsided in the wild by some obscure class of stellar tantrum. So there's a kind of arms race going on. Better simulations of real kilonovae, better catalogs of imposters, better classifiers that can say, okay, this one is worth waking everyone up at 3 a.m. for. The stakes for all this gear up aren't just more pretty light curves. Right now, almost every sweeping statement we've made about neutron star mergers and heavy element production is anchored to AT 2017 GFO. That's like judging an entire species based on one very photogenic individual. If Rubin, Roman, JWST, and the next LIGO, Virgo, Kagra runs start delivering dozens of well-characterized kilonova, two big possibilities open up. In one, AT 2017 GFO turns out to be fairly typical. Similar ejecta masses, similar color evolution, similar association with short GRBs and structured jets. In that case, we gain confidence that our current story, mergers as major R-process factories, kilonova as standard sirens, remnant behavior constrained the way we think, is on the right track. In the other possibility, AT 2017 GFO is kind of an oddball. Maybe most kilonova eject less mass or more. Maybe many are much bluer or redder. Maybe the rate of mergers that actually produce bright kilonova is lower than we assume, or tied to particular kinds of binaries or environments. Maybe some are powered by long-lived magnetars more often than we think. A big diverse sample could force us to rebalance the heavy element budget all over again, dial back or amp up the role of mergers compared to exotic supernova, and rewrite our neat origin story for gold again. The real plot twist might be sitting in the future Rubin data stream, a pattern we haven't anticipated, a subclass of kilonova we haven't named yet, or a systematic difference between early universe and present-day mergers. AT 2017 GFO was the pilot episode that proved the show was worth making. The next generation of kilonova hunters, on the ground and in space, are about to binge the rest of the season, and there's a very real chance the main character we've built in our heads is not who the series is actually about. For most of this story, we've been hanging out at huge scales, galaxies, gigaparsecs, and tidal tails of neutron star shrapnel. Time to bring it crashing down to something much smaller and much weirder. Your body is a walking chemical history book. Around 60% of you by mass is oxygen, mostly in water. Toss in hydrogen, carbon, and nitrogen, and you've explained almost everything in your cells. Those light elements come from the Big Bang, for hydrogen and some helium, and from generations of stars that lived and died in fairly ordinary ways. Core collapse supernova, stellar winds, the usual stellar cookbook stuff. That's the we are stardust part of the story, and it's true, but not all of you is stardust in that generic sense. Tiny but crucial ingredients, like the iodine in your thyroid, some of the heavier trace elements in your blood, and maybe the gold in a tooth filling or ring, almost certainly owe their existence to R-process events, the kind of extreme neutron-rich explosions that kilonova embody. Astrophysicists can actually test this kilonova dust in your veins idea using chemical evolution simulations. You take a model galaxy, sprinkle in star formation, add normal supernova, and then inject neutron star mergers at a rate similar to what LIGO and pulsar populations suggest. Each merger ejects a blob of R-process rich material, kilonova style ejecta, with yields tuned to match something like AT 2017 GFO. Let the model run for billions of years. Track how elements like europium, a classic R-process tracker, build up in stars of different ages and in different parts of the galaxy, and then compare to real observations of Milky Way stars. The neat result is that when you include neutron star mergers with realistic delays and yields, you can reproduce the observed europium abundances in old halo stars and the general R-process pattern we see in the local universe. In other words, the numbers hang together. Mergers happening at rare but steady intervals can indeed paint the galaxy with the right amount of heavy stuff. That doesn't mean kilonova have completely monopolized the heavy element storyline. There are still exotic alternatives lurking in the wings. Some models invoke magneto-rotational supernova, massive stars that collapse while spinning rapidly and threaded by strong magnetic fields, as additional R-process sites, especially in the very early universe when neutron star binaries might not have had time to merge yet. Others point to collapsars, where a massive star collapses into a black hole with an accretion disk and launches jets. The disk winds in those systems could also be neutron-rich enough to run the R process. The current mood is that neutron star mergers and their kilonova are the main actors, especially for a lot of the gold, platinum, and European budget, but a few rare exotic core collapses may be cameo guests that help explain some of the most extreme R-process signatures in very old metal-poor stars.
Still, even if mergers share the stage, the personal narrative lands the same way. Picture this. Billions of years ago, somewhere in the Milky Way's young disk or halo, two neutron stars that had been quietly orbiting each other for ages finally hit the fatal last orbits of their inspiral. They chirped in gravitational waves, maybe launched the gamma ray burst, and lit up in a kilonova. In the debris of that explosion, a cloud of R-process nuclei cooled and expanded, including a spray of freshly minted gold atoms. Over tens or hundreds of millions of years, that cloud mixed into the galactic gas, which later collapsed to form a new star-forming region, the cradle that would eventually birth the Sun and its planets. In the dusty protoplanetary disk around young Sun, a few of those gold atoms stuck to the grains that became Earth. Geological processes carried them into an ore vein. At some point, humans dug that vein up, refined it, shaped it, sold it, and now one of those atoms is in a ring on someone's finger, tapping idly on a keyboard while they watch a video about kilonovae. That's the real emotional payload, hidden behind all the gravitational wave plots and nuclear reaction networks. When we say you are stardust, we're telling only half the story. A tiny but profound fraction of you is kilonova dust, or dust from some similarly extreme R-process event. The iodine atoms your body needs to regulate metabolism, the trace heavy elements in your bones, the shiny metal you associate with wealth and meaning, some of those were assembled in environments so violent that matter itself was being ripped out of neutron stars and rebuilt from scratch. The rarest explosions in the universe are not just remote curiosities. They have literally written part of the periodic table inside you, and on you, and around you. By now, you might be forgiven for thinking the universe is just full of luminous, gold-forging, multi-messenger spectacles. But if you listen to LIGO and Virgo's greatest hits playlist, most of the tracks are actually much simpler and much darker. The majority of gravitational wave detection so far are black hole mergers, huge thunderous events in space-time that, from the point of view of ordinary telescopes, might as well not exist. They shake the universe harder than neutron star mergers do, but they leave almost nothing for your eyes to see. A binary black hole merger is, in some sense, the cleanest possible gravitational wave source. Two regions of curved space-time orbit each other, with essentially no material outside their horizons. There's nothing to shred, nothing to heat up, nothing to fling outward. As they spiral together, they emit gravitational waves, the frequency rises, they merge into a single larger black hole that rings like a struck bell for a moment, and then silence. No shockwave plowing through stellar layers, no radioactive debris cloud, no jets punching through gas. With nothing outside the horizons to light up, electromagnetically you expect basically zero. No gamma ray burst, no optical transient, no radio flare. And that's exactly what we see. Almost all black hole mergers show up only in gravitational waves. The rest of the spectrum stays stubbornly blank. That contrast is part of what makes neutron star mergers so valuable. They're messy. Neutron stars actually consist of matter, so when they collide, there's something to tear up and rearrange.
But even in mixed systems, neutron star plus black hole, it's not guaranteed that you get a kilonova. Events like GW 230529, which seems to involve a neutron star merging with a relatively low-mass black hole, in that interesting 2.5 to 4.5 solar mass gap between typical neutron stars and standard stellar mass black holes, highlight how delicate the conditions are. Whether such a system produces a bright kilonova depends mainly on two things: the mass ratio and the black hole spin. If the black hole is too massive compared to the neutron star, or if its spin isn't oriented in a way that helps, the neutron star may simply plunge straight through the tidal disruption radius and get swallowed whole. In that case, almost no material is left outside the black hole's horizon after the merger. No debris disk, no tidal tails, no neutron-rich flung-out matter, which means no kilonova, or at best, a very faint one. You still get a perfectly respectable gravitational wave signal, but nothing to light up telescopes. To tear off neutron-rich chunks and make a proper kilonova, the black hole has to be just right, low enough mass or spinning rapidly enough in a favorable direction that its tidal forces rip the neutron star apart before everything crosses the point of no return. Only then do you get the radioactive confetti show. That's why pure neutron star mergers are such multi-messenger gold. They almost guarantee a complex outcome: gravitational waves from the inspiralan merger, a possible short gamma ray burst if a jet forms and points near us, a kilonova glow from the radioactive ejecta, and longer-lived X-ray and radio emission as jets and outflows slam into the surrounding medium. It's as if the universe decided, in a tiny fraction of its collisions, to turn on subtitles, director's commentary, and the behind-the-scenes featurette all at once. But it's important to remember that these talkative events are the exceptions, not the rule. Most of the universe's most violent collisions are effectively dark to traditional astronomy. Black hole mergers hoover up their own mass and leave only ripples in space-time. Many neutron star black hole systems probably swallow their neutron stars too cleanly to give us a show. Even some neutron star mergers might be too far, too faint, or too off-axis for us to catch their light with current telescopes. We live in a cosmos where countless massive objects slam together all the time, scream in gravitational waves, and vanish without a photon for us to see. Kilonovae are the rare cases where everything lines up just right. There's matter to shred, the geometry and masses favor substantial ejecta, the jets, if any, aren't completely hidden, and we happen to be watching in the right place, at the right time, with the right instruments. They're the tiny subset of cosmic car crashes where the airbags deploy with fireworks and confetti instead of just a thud. For science, those few noisy, luminous collisions punch far above their weight. They're how we sneak into the physics of nuclear matter, heavy element production, jet formation, and even cosmic expansion, using the rare times when the universe decides to keep its most violent moments entirely in the dark.
GW 170817 shouldn't be this important, and yet here we are, treating one cosmic car crash in a sleepy galaxy as if it were the Rosetta Stone of high-energy astrophysics. And in a very real sense, it is. From that single event, we've already pulled out constraints on the equation of state of neutron stars, weighed how squishy ultra-dense matter can be before it gives up and collapses, watched a kilonova's R process glow confirm where a huge fraction of the universe's gold and platinum come from, measured the speed of gravity to absurd precision, and even taken a first wobbly step toward measuring the expansion rate of the universe with standard sirens. One merger, one kilonova, and we've edited half a dozen chapters of the cosmic textbook. But if GW 170817 is our Rosetta Stone, it's also a slightly annoying one, because we don't yet know how representative it is. Was this a typical binary neutron star merger, the platonic ideal we should use as our template? Or was it a bit of a weirdo? An unusually nearby, unusually well-oriented, unusually ejector-rich outlier that just happened to be the first one we ever caught? We don't yet have a map of the full parameter space, the true distribution of ejecta masses, the range of viewing angles and how they skew the apparent brightness and color, the variety of remnant lifetimes from prompt black hole to brief hypermassive neutron star to long-lived magnetar. Even the detailed element-by-element composition of the ejecta is still being fought over in papers. The spectra scream heavy stuff in lanthanides, but pinning down exact abundances is an ongoing cage match between atomic physics and telescope sensitivity. That's why future observing runs, 04, 05, and whatever comes after, matter so much. The LIGO-Virgo COGRA collaboration has been ratcheting up sensitivity, expanding the volume of space in which they can hear neutron star mergers and mixed systems like neutron star black hole pairs. New events like GW230529 hint that the zoo of compact object mergers is more diverse than our neat diagrams suggest, and each detection comes with a standing invitation to every telescope on Earth and in orbit, quote, "If you can see anything in this patch of sky, look." The dream is a growing set of GW170817-like cases, gravitational waves plus kilonova plus afterglow across a range of masses, spins, environments, and distances. Only then do we get to stop extrapolating wildly from one pristine data point. There's a kind of meta-level audacity in what we're doing right now, and it's worth calling out. Humans are, with a mostly straight face, rewriting the origin story of the heaviest elements, constraining the behavior of matter at densities beyond any lab, revising our ideas about gamma-ray bursts, and building a third independent way to measure the expansion of the universe largely off the back of a handful of events, and especially one that happened in August 2017. This is science operating at the edge of, is this enough data to be sure, and pushing forward anyway, because the alternative is to wait a few million years for more kilonovas to happen nearby. It's both reckless and completely rational. When the universe gives you one immaculate experiment, you squeeze it for all it's worth. And yet, for all that we've learned, most of the map is still blank. We don't know how common magnetar-powered mergers really are. We don't know whether the early blue component in AT 2017 GFO is standard or unusual. We don't know how often neutron star black hole mergers actually shred the neutron star versus swallowing it cleanly. We don't know whether the Milky Way's specific heavy element budget is normal or a bit quirky compared to other galaxies. We're in that awkward phase where the first clear signal has collapsed a bunch of old possibilities, but opened a corridor of new questions stretching off into the dark. The strangest part, and the bit that's easy to miss, is how exquisitely timed all of this is. For most of cosmic history, kilonovas have been going off in total anonymity. Two neutron stars spiral together, merge, flash briefly in blue and red, spray out heavy elements, and fade. No one is watching. No one is there to notice that in that anonymous explosion, enough gold and platinum were forged to one day plate spacecraft, wire electronics, or decorate some primate's hand. Only in the last tiny sliver of time has one particular species on one rocky planet built lasers stable enough to measure space-time stretching by less than a proton's width, telescopes sensitive enough to catch a fading red smudge in a distant galaxy, and software clever enough to say, "That one, follow that one." You're alive exactly in that sliver. You exist at the moment when the universe's rarest explosions are finally being dragged out of obscurity and identified as the authors of part of the periodic table inside you. For billions of years, kilonovas shaped galaxies and planets in the dark, unobserved. Then, once, in 2017, one of them happened to go off close enough and clean enough for us to see properly. And we realized that the rarest fireworks in the cosmos had been quietly writing their signature into our bones, our technology, and our jewelry, all along. Everything since then, the papers, the arguments, the new detectors coming online, is humanity collectively saying to the universe, "Run that again. We know what to look for now." This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.